Welcome everyone. So today we're going to be talking about the alpha beta pruning. This is within the context of artificial intelligence, and we are studying about the adversarial search. Okay, so let's talk about this. Within this, we're really going to focus just on the alpha beta pruning. But again, this is within the context of adversarial search, where we understand what are the types of adversarial games, what's the basic nature, what's the value of a state, and then we'll focus on the alpha beta pruning here today. Okay. So within the adversarial search, we're talking about a zero-sum deterministic game, commonly known as competitive games that we play, such as tic-tac-toe, chess, checkers, Go, etc. Now, one of the things that here I would start by articulating is that here we should think about result as a perspective-less quantity. By that, what we mean is that, of course, both the players are trying to win, but we will think about the result as not from the perspective, but rather we'll just say that the first player is trying to maximize the result and the other player is trying to minimize the result. And this articulation will help us in some of the items that we are going to do today. Okay. So as we continue to talk more about it, let's remember we are thinking about result as a perspective-less quantity. So again, we'll have two different agents. Agents will have opposite utilities because we are talking about the zero-sum deterministic games. That's not true for all games, but for the zero-sum deterministic games, agents have opposite utilities, the values and outcomes. And we will think about a single value that one agent is trying to maximize, the other is trying to minimize. So it's an adversarial situation, purely computation. And the notation that we will use is that there are states S, and we will start with the S0, the initial state, which is, for example, the empty board or the initial board in the case of chess. The players are 1 to 2, and they usually take turns, although you can have n players as well. The action that a player takes is within the set of actions A, and we call transition function, which takes a state, takes an action, and results in a new state. So for that reason, we call transition function is a mapping from S cross A, the Cartesian product of S times A, to the result, which is an S. Similarly, the utility here is that we will have for each state, the player P and the final result R. The solution that we're looking for is for a player is a policy which defines, given a state, what action should they take. Again, so this is a mathematical notation of the concepts that we would normally already understand. So let's think about the basic nature of an adversarial search. The basic nature is that of recursion, where we have to assume the opponent will also try to make the best possible move. So the agent in blue is going to try to maximize the result. Then agent in red, the next agent, the opponent, will try to find a way to minimize the result. And then still, we will try to maximize the result, and so on and so forth, until we can result into a terminal state here. The terminal state could be, in the example of case of chess, could be like when one side has checkmated the other one. So mathematically, we would write this as a minimax value, that the state under agent control, it is going to think about all different states, all possible moves that we can make, and we're going to try to make the best possible move. So in other words, from all the values of the states S prime, where S prime is a successor of the current state that we are in, we will take the maximum. And similarly, the opponent will try to find whichever state we put them into. From there, whichever state they can choose, they will try to minimize the result. For the terminal states, again, when one side has 1, we know the value of those states here. Okay, so this is the adversarial search, the minimax algorithm. In the minimax algorithm, it is going to be what we call a minimax search, which is a state space search tree. Players are going to alternate turns, and each node, we're going to compute each node's minimax value, the best achievable value against a rational or the optimal adversary. So the values are going to be computed recursively. So for the terminal values here, part of the game, if we have these values, the opponent is going to choose here the state that minimizes the result. So that's going to be 2. Similarly here, 5. So within these two, we will choose the one that maximizes, and we will take this one. So again, this basic nature of the adversarial search should be clear to us. For example, here we have a way to reach 8, but we don't make that move because we know if we make that move, the opponent will take this move, which will give the value of 2. And that doesn't maximize it for us. So we will try to go in this direction. The opponent will say, okay, well, between these two, I'm going to take this direction. So we will reach the maximum value of 5 here. So this is the basic nature of adversarial search here. Let's talk about a minimax example a little bit further. Let's suppose this is a 2-level tree here, and these are the values of these terminal states here. So what will be the value of each min node here and a max node here? Again, the min nodes are represented with an inverted triangle. Max nodes are represented with a regular upside triangle here. So here we will take the minimum, and we will take the maximum. So if we do that, then we're going to, of course, reach that this is equal to 3, this is equal to 2, this is equal to 2, and the maximum is equal to 3. So because it's in our control, we're going to say, okay, we'll go here. Here the opponent will make the move that minimizes the result for us, which will be a 3, but overall we'll still be maximizing here. Now we can also try to go here thinking there's a 6 here, but when we do go here, the opponent will choose the state that minimizes, which will be this 2, and we'll end up with a 2, so we will go here. So this is the minimax algorithm. By itself, it's simple. We're simply doing a search here. Now, the concept of this particular mini video here is that of alpha beta pruning. So let's try to do that. So what is alpha beta pruning? In very simple terms, it's a technique that optimizes this minimax algorithm by eliminating branches that do not need to be explored. So we are trying to eliminate branches that we think we don't even need to know. Sometimes it's easier to think about in terms of no need to compute, as opposed to computing and then pruning. Sometimes the word pruning can confuse some students who think about, okay, we're going to prune this subtree, but if you have already computed it, then you have already spent the computation time on it. So the question we should ask ourselves is, which of the values we do not care about? So in other words, when we want to do alpha beta pruning, we should think about, we don't know these values. Should we compute them or should we not compute them? So at this point, I've covered all the values and we don't know them. So what should we do? Do we need to compute this value? Yeah, if we don't know this value, we won't really be able to show what's the minimum here and what's the best way to go. So we have no option but to compute the first value here. So we compute it, then it's 3. Now we know that the value of this node, this min node, is less than equal to 3, because here, even if it turns up to be 1,000 or 100, the opponent will choose the minimum one, 3, and that will be 3. Now if this turns up to be -5, the opponent will choose the -5. So therefore, all we can say is the value of this node is less than equal to 3. But we don't know the exact value yet. So should we still continue to compute? I think so, because just because we know it's less than equal to 3, we don't know how to maximize. So we are going to go ahead and compute the next node as well. This comes up to be 12. Now this doesn't really give us new information. This still shows that this is less than equal to 3, but we didn't know, so we had to compute it. In fact, we don't know about the third node either. Should we compute it? Should we not compute it? We will have to compute it, because if we don't compute it, we're not able to make a determination of this one. So let's go ahead and compute it. So once we compute it, Now we know this value of this node is really 3, not less than equal to 3. Now we know it is actually equal to 3 here, so we can go ahead and write it. Now, can we go ahead and eliminate the others? I don't think so, because we still have to figure out what's the value of these nodes here. Now, here we can already reach a mini conclusion that the value of this top node is at least equal to 3, because we already have a state in which we will get 3. So if nothing else, we'll have that as our one basic move as well. Now, if we can reach a 5 here or a 7 here, certainly we will try to do that, but we don't know if that's possible. So all we know is the value of this node is at least equal to 3. This is equal to 3. For this node is at least equal to 3, greater than equal to 3 in other terms. And these ones we don't know, so we cannot eliminate anything yet. So let's go ahead and compute it. So we compute 2. Now we have an interesting circumstance. Now we can say the value of these nodes, the value of this node here, this min node, is less than equal to 2. And therefore, we know that we actually don't really care about these two nodes. We don't care because in either case, we're not going to take this one. The value of this min node is less than equal to 2, and we're not going to go in this direction anyway. We're going to go here, or maybe the third one, but certainly not the second one. And that allows us to prune these two nodes here. We don't know what those values were, what those values are going to be. We simply write that this is less than equal to 2, and therefore we have pruned these two nodes here. Now, what about the third one? Should we compute? Let's think. Let's suppose all of them are 5. We don't know, but let's suppose all of them are 5. This will be a 5, then that will be a 5. So therefore, and maybe that's the direction we want to go, so maybe we should compute it. Now, it's also possible all three are minus thousands, minus 1,000, minus 1,000, minus 1,000, in which case this will be a minus 1,000, in which case we will take this 3, and there we have it, that we don't really know whether we need it or not, which means we basically need it because we're not able to eliminate it. So let's go ahead and compute the next one. Oh, this is 14. Now, if this is also 14 and this is also 14, this will be a 14, and that's the direction we'll go. So we don't know it yet, so let's go ahead and compute it. Okay, so this is a 5. Now we know that the value of this min node will be less than equal to 5. It won't be 14 for sure. It'll be less than equal to 5. But if this one is 5, hypothetically, then this will be 5, and then this will be 5. So we don't know, so means we should go ahead and compute it. So we go ahead and compute it. Okay, this turns out to be a 2. So therefore, the value of this min node turns out to be 2, and the value of this min node, this max node, turns out to be 3. We have to compute it, but we were not able to eliminate these, right? So we go ahead and compute this 2 and 3, and we don't eliminate anything else because we could not rationalize eliminating anything else. Now, in this case, we remember that this minimax example represents a 2 by 9 saving. There were 9 nodes here, and we were able to eliminate 2 of them. So it represents a good 2 by 9 saving in execution time here. If we look at the implementation, there are actually, before the implementation, let me go back one more moment and make one point here, that if this was in a different order, 2, 5, and 14, we would have been able to eliminate more. But we don't control the order, or at least we have not talked about how to use the order to our advantage. In this order that was presented to us, we could not have eliminated 2 because we only came to know about 2 later. So firstly, we computed this 14, that came up to be 14. We had to keep it. Then we computed 5. So we spent the time in computing that 5. Then we spent the time in computing the 2. And then we reached it, so we were not able to eliminate anything else here. Okay? And therefore, we have that 22%, that's 2 out of 9 savings in execution time, which is still pretty good. Okay? So if we think about the implementation, all this rationalization is actually very straightforward. It is not here in the video, we're talking step by step on how to decide whether eliminate or not. But when we are writing an algorithm, it's all very straightforward, that we simply choose we simply define these values here as the alpha and the beta. Alpha is the max's best option on the path to root. Beta is the min's best option on the path to root. Again, alpha is the max's best, beta is the min's best. And when you're trying to maximize the value for each successor state here, if the value turns up to be more than beta, you just return. That means you don't compute anything more, right? Otherwise, you compute. So this is the return statement represents our favorable scenario where we are able to skip the computation of other values. The value here is in this value function, value successor with these limits alpha and beta. So if the value of v is greater than or equal to beta, we just simply return v. We don't go any further. Otherwise, we continue and we keep doing value. Similarly, for the min value, we do the same thing. If v is less than or equal to alpha, we immediately return. We do not continue with the rest of the for loop here. So we have the for loop can go on up till the number of times, which is the branching factor. In this case, if we are able to return, that represents a saving of alpha beta implementation. And that's really the main idea. The main idea of alpha beta overall is that the pruning should have no effect on the minimax value computed for the root. Now you could have some values, the intermediate values, which might be wrong. For example, we were only able to say that something is less than or equal to 2 as opposed to knowing exactly what it was. Maybe there was a smaller value down there, so which was 1, but we were just able to argue that we don't need to compute it in any way. In that sense, this is an example of meta reasoning. Meta reasoning in this case means that we are computing about what we should compute. So that's meta reasoning here. And here comes the point about the ordering. A good child ordering can improve the effectiveness of pruning. As we saw, we had an example with 14, 5, and 2, in which case we were not able to eliminate anything. 2, 5, and 14, we would have been able to eliminate if we had seen the 2 before, because we would say that, hey, the min node is going to be less than or equal to 2. No point calculating 5 and 14 because the max node was already 3. Okay. So overall, the time complexity of this can be improved of minimax search, which is b power m. This makes it about half of that, which is b power m by 2. Or in other words, you can double for the solvable depth here. Okay. Now it doesn't make that this is now suddenly linear time or polynomial time. It is still exponential time. But there is improvement in what we are able to do. And an improvement that comes sort of for free. Okay. An improvement that comes sort of for free. Their alpha beta implementation itself is straightforward. Just keep those terms, alpha and beta, keep those limits. And then whenever you can, you simply eliminate it. And that's what you have. So that's really what I have in this particular lecture, this particular mini video here. Watch it a couple of times if you have to. But the concept of alpha beta pruning within the context of adversarial search is super important. And you might find a couple of quizzes here. So please practice those as well. Sometimes, again, if I can go back, I will try to go back to this particular slide here so you can think about that you should think about in terms of no need to compute, as opposed to thinking that, oh, I'm going to prune this node. Well, if you've already computed it, that's not pruning. You've already spent the time to compute it. So think about which values we don't even care about. Okay. So that's all we have for today. So continue learning.